In this video, I'm going to show you how carbonyl compounds like ketones and aldehydes can react with alcohols. This is a very important reaction biologically, and at the end of this video, I'll show you how this reaction is used in sugar chemistry or carbohydrate chemistry, like linking glucose molecules together. Let's jump right in. This is an aldehyde. It's a carbonyl with a hydrogen attached. If I react it with an alcohol in the presence of acid, it makes this compound. Hydrogen, carbon, and the R group are still here, but instead of C double bond O, these two carbon-oxygen bonds, now my two carbon-oxygen bonds are split and they look a little different. This alcohol group is now one of the oxygens with an R group, OR, and the other one is an OH group. If I further react this with alcohol and acid, this OH group on this compound can be replaced with O carbon, OR. We call this compound that comes from an aldehyde with two OR groups on it, oxygen-carbon groups, an acetal. And we call the halfway point, halfway to the acetal, the hemiacetal. So this is what you need to get in your head. Two carbon-oxygen bonds, two carbon-oxygen bonds, two carbon-oxygen bonds. But my carbonyl turns into the hemiacetal, an OH and an O carbon coming from my alcohol. And if there's more alcohol, you can get O carbon and O carbon, two of them on there. Aldehyde, hemiacetal, acetal. This reaction also works with ketones. I'll just use carbons on there for ketones. It can react with my alcohol. The hemi, halfway there will be this carbon has an OH on it and an OR, methyl, ethyl, whatever. Depends on what alcohol I use. If this keeps going with more alcohol, this OH of the hemi becomes OR, and this OR is still there. So these are also called acetals or hemiacetals. But the old school way of naming these, just so you know, you might encounter these. If we start with a ketone, some people call this final compound a ketal. That's older language, but you might still hear it, a ketal. And of course, halfway there will be the hemiketal. So ketones become hemiketals, become ketals, or the newer language is just to use the acetal language. Okay, so that's the first thing in your head. Two carbon-oxygen bonds, two carbon-oxygen bonds, two carbon-oxygen bonds. OH and O carbon from my alcohol, and then two O carbon groups, OR groups for the acetal. Now let me show you a little trick how we can use this acetal to our advantage. Let's say I want to do this reaction. I have two carbonyls, a ketone, carbon, 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 and an aldehyde. There's a hydrogen on my carbonyl. And let's say this is the compound I'm trying to make. I want this carbonyl to become an OH, but I want my aldehyde to stay the same. And you might think, okay, in order to take a carbonyl and turn it into an alcohol, I need a reducing agent like sodium borohydride. Or maybe I use LAH. The problem with these reducing agents is, of course, both the ketone and the aldehyde would react with it. So I'd end up with the alcohol I'm after, but I would also reduce my aldehyde to an alcohol. So how do I prevent this from happening? Well, one of the ways we do such a thing is we hide this aldehyde for a little bit, do the reduction reaction, and then bring the aldehyde back. When we hide it, we call that protecting it. We protect it. So here's one way we do it, using my acetal chemistry. We start with ethylene glycol. There's two carbons, ethylene, with two OH groups, so glycol, ethylene glycol. You have a little bit of acid in there. And between ketones and aldehydes, we find that aldehydes react faster with ethylene glycol. So what happens is my ketone stays the ketone, and my aldehyde part becomes this acetal. So I preferentially protect or hide the aldehyde and make an acetal out of it. Now, once it's protected, I can do my reduction. So I add my sodium borohydride. This is not a carbonyl anymore, so it doesn't get reduced. Only my ketone does. So it becomes an alcohol. And I still have this protected acetal. Looks a little bit like an alien face. It's really surprised, big eyes. Then what I want to do is I want to deprotect it. Take this back off and turn it back into the carbonyl. So the best way to do that is you add some water and acid, you hydrolyze it, and you can turn it back into the aldehyde. And that's the workaround whenever I need to protect an aldehyde over a ketone. And aldehydes get protected first because they stick out, they're on the end of the molecule, they react a little faster than do ketones. Now let me show you how this reaction happens in biology. This molecule is D-glucose, a sugar. And sometimes they'll show it to you this way. They draw it in a straight line. You have an aldehyde on there. Look at all of these alcohol groups on here. And what happens is my carbonyl can react with one of these alcohols. And the first one it reacts with, the carbonyl reacts with this alcohol. So let me redraw this with this carbonyl next to this alcohol. So I've taken this D-glucose molecule, I laid it down on its side. So here's the aldehyde part from the top, now on the right side. And all of these OHs that were on the right side, when I lay it down, will point down. And this one that's on the left side, when I lay it down, will point up. So here's my aldehyde. This alcohol group points down. It's on the right, so it points down. This one's on the left, so it points up. This one's on the right, so it points down. My CH2OH is this one. And this alcohol, I twisted this carbon so this alcohol lines up with this aldehyde. So they're close to each other. So here I have an aldehyde. It's going to react with an alcohol. And we remember that aldehydes react with alcohols, with acid around, to make hemiacetals. So one of the carbon-oxygen bonds, the oxygen gets protonated to be an OH. And the other OR group comes from the alcohol. So when I react this alcohol with this aldehyde, it makes this cyclic form of glucose, or the sugar. And this is often how biologists will draw this. So this oxygen is right here, and this carbon right here is the one that has the only carbon in this entire molecule that has two carbon-oxygen bonds. It's this right here. So this carbon has an OH group because it's a hemiacetal, and an OR group from the alcohol. So this carbon is called the anomeric carbon in biology, and the anomeric carbon is the hemiacetal carbon. Now we know that hemiacetal OH groups can react with more alcohol to make more OR groups, or an acetal. So this OH group is the one that's very reactive. Out of all these alcohol groups, this one on the anomeric or hemiacetal carbon is the one that can react with other alcohols to make all kinds of other molecules. What other alcohols could be around? Well, it could be another sugar. Look at all of the alcohol groups. So it could react with another sugar like glucose or galactose, and can make, that's what lactose is. Lactose in milk, that sugar, is a glucose and a galactose stuck together. So sugars can link together through that OH group of the hemiacetal to make acetals. We call those glycosides in biology, but we call them acetals in chemistry. So I wanted you to know that this is important in biology, but I don't want you to worry too much about that right now. What I would do is focus on carbonyl to hemiacetal to acetal. I hope that was helpful. Think about subscribing to the channel so you can follow more of my videos, because I'd love to help you with your organic chemistry.